Directed lines and uniqueness of direction cosines. Welcome, everyone. Let's begin our discussion on directed lines and the uniqueness of direction cosines. To start, let's quickly recap what we covered in our previous subsection. We learned that the direction cosines of a line are simply the cosines of the three specific angles, alpha, beta, and gamma, that the line makes with the x, y, and z axes, respectively. Now, as we move into this new topic, we need to consider a fundamental geometric property of any line. A line, by its very nature, extends infinitely in two opposite directions. This brings us to a bit of a mathematical dilemma. Because the line goes both ways, it introduces a specific challenge when we try to define a single, unique set of direction cosines. As we will see in the next slide, this property actually creates some ambiguity that we'll need to resolve using the concept of a directed line. The ambiguity of a standard line. Now, let's look at slide 2, where we explore why we run into a bit of a problem with a standard line. Think about a line in three-dimensional space. Unlike a line segment, a geometric line doesn't have an inherent start or end point, it just goes on forever. Because of this, if you were standing anywhere on that line, you could choose to move in one direction, or you could turn around and move in exactly the opposite direction. This brings us to a mathematical dilemma. Since there are these two distinct, opposite directions along the same path, there are actually two different possible sets of angles that the line can make with our x, y, and z coordinate axes. As a result, we find that a single, standard line actually possesses two different sets of direction cosines. This ambiguity is exactly why we can't rely on a standard line if we want a single, unique answer. And that is why, as we will see in the next slide, we need to introduce the concept of a directed line. The concept of a directed line. Now, you might be wondering, how do we solve the problem of having two different sets of angles for the same line that we just discussed? To eliminate this ambiguity and ensure that every line has one, and only one, unique set of direction cosines, we introduce a new concept called a directed line. Think of a directed line as a line that has been assigned a specific direction of motion, or what we call an orientation. It's no longer just an infinite path. We've essentially placed an arrow on it to show which way is forward. Once this direction is fixed, the angles alpha, beta, and gamma become unique, because we are only looking at the angles relative to that specific direction. Because these angles are now fixed, we use a standard notation to represent these unique direction cosines. We typically denote them using the lowercase letters L, M, and N specifically. L equals cosine alpha, M equals cosine beta, and N equals cosine gamma. As we move to the next slide, we will see exactly what happens to these values if we decide to flip that direction around. Reversing the direction. Now that we understand how a directed line gives us a unique set of direction cosines, let's look at what happens when we change that direction. If we decide to reverse the direction of our directed line, let's call it line L, the new direction angles won't be the same. Instead, the new angles will be the supplements of our original angles. Let me walk you through the step-by-step logic so you can see how this works mathematically. First, let's assume our original angles are alpha, beta, and gamma. Second, when we flip the direction to the exact opposite side, the new angles become pi minus alpha, pi minus beta, and pi minus gamma. Third, we can use a very handy trigonometric identity that you should all remember. The cosine of pi minus theta is equal to negative cosine of theta. Applying this to our specific angles, the cosine of pi minus alpha becomes negative cosine of alpha, which is simply negative L similarly. The cosine of pi minus beta becomes negative cosine of beta, or negative M, and finally, the cosine of pi minus gamma becomes negative cosine of gamma, which is negative. So, to wrap this up, the key takeaway here is that reversing the direction of a line simply results in the signs of all its direction cosines being reversed. It's as simple as that. The values stay the same, but the plus signs become minus signs, and vice versa. Real-world analogy, navigation. Now, to help you visualize this concept of direction and ambiguity, let's step away from the coordinate axes for a moment and look at a real-world analogy involving navigation. Imagine a straight road that connects two different cities. Let's call them City A and City B. If you are driving on this road specifically from City A towards City B, you are moving in one very specific, fixed direction. If we were to measure your movement relative to north, east, and up, your direction cosines would be fixed to a specific set of values. However, if you decide to turn your car around and travel from City B back towards City A, notice what happens. You are still on the exact same physical road. The path, or the line, hasn't changed at all. But your direction of travel is now exactly the opposite of what it was before. In mathematical terms, this is exactly what we discussed in the previous slides. Your orientation has flipped. Even though the path remains the same, your direction cosines will have changed their signs. This perfectly illustrates why we need the concept of a directed line to avoid confusion, which we will see applied in a concrete numerical example in the next slide. Illustrative example. Now that we've understood the theory behind how direction changes, let's put it into practice with an illustrative example. Suppose we are working with a directed line, let's call it L, and we are given that its direction cosines are L equals 1/3, M equals 2/3, and N equals 2/3. To solve this, we'll follow a simple three-step process. In step 1, we first identify our starting point. Our current set of direction cosines is 1/3, 2/3, and 2/3. Next, in step 2, we need to determine what happens if we decide to reverse the direction of this line. As we discussed in the previous slide, reversing the direction means we are replacing our original angles, alpha, beta, and gamma, with their supplements. Finally, in step 3, we apply the sign change. Based on the trigonometric identity we just learned, where the cosine of a supplementary angle is simply the negative of the original cosine, we can calculate our new values. Our new L prime becomes negative 1/3, our new M prime becomes negative 2/3, and our new N prime becomes negative 2/3. So, as you can see, our new set of direction cosines is negative 1/3, negative 2/3, and negative 2/3. Notice how every single sign has flipped. This leads us directly into our final summary of the key takeaways. Key takeaways. First, remember that a standard, geometric line is inherently ambiguous. Because a line extends infinitely in two opposite directions, it actually possesses two different sets of direction cosines. To solve this problem and achieve mathematical precision, we use the concept of a directed line. By assigning a specific orientation or direction of motion to the line, we ensure that we have one, and only one, unique set of direction cosines, which we denote as L, M, and N. Now, what happens if we flip that direction? As we saw in our step-by-step derivation earlier, reversing the direction changes our original angles, alpha, beta, and gamma, into their supplements. In radians, this means the new angles are pi minus alpha, pi minus beta, and pi minus gamma. Finally, the most important mathematical shortcut to remember is the transformation itself. When you reverse the direction cosines undergo a simple sign change. Mathematically, we represent this transformation as the set L, M, N becomes negative L, negative M, and negative N. All right, let's bring everything we've discussed today together. This slide serves as a summary of our key takeaways. Before we move on to some common pitfalls to avoid, I want you to ensure you've internalized this relationship between direction reversal and the sign change of the cosines. Common mistakes. First, be careful not to confuse a geometric line with a vector. It is a very common mistake to treat them as the same thing. Remember, a vector inherently possesses a built-in direction, but a standard geometric line does not. It simply extends infinitely in both ways. As we discussed earlier with the concept of the directed line, you must explicitly specify an orientation or a direction of motion if you want to arrive at a unique set of direction cosines. Second, watch out for errors when calculating supplementary angles. When you reverse the direction of a line, some students mistakenly believe that only one of the signs will change. However, as we saw in our step-by-step logic on slide 4, because the entire axis of the line is being reversed, the direction angles all become their supplements. This means the signs of all three direction cosines, L, M, and N, must be flipped simultaneously. It is a total sign reversal. L, M, and N become negative L, negative M, and negative N. Finally, a small but important note on notation. When you are calculating these supplementary angles, please ensure you use radians, specifically using the pi notation, rather than using degrees like 180 degrees. To stay consistent with the formal NCERT notation and mathematical standards, always stick to pi minus alpha, pi minus beta, and pi minus gamma. Now, before we wrap up today's lesson, I want to highlight a few common pitfalls that students often encounter when working with direction cosines. Paying attention to these will help you avoid losing marks in your exams. Keep these points in mind, and you'll be well on your way to mastering 3D geometry.